Okay. So good morning. My name is Qiyue Qian. Since my name may be hard to pronounce for many of you, so it's okay to just call me Qiyue as you like. And it's my great honor to give this talk today. I'm a third year PhD student from Tsinghua University. Today, I will introduce the systematic search for the free-floating planets in KMTNet microlensing survey, and including our new full-frame image reduction pipeline, some recent results, and the future's perspective. And my collaborators are listed here. So, as introduced by Murat in the previous talk, due to the low mass of free-floating planets, when they act as the lenses, these microlensing events can have extremely short time scales, typically less than 1 day, and tend to show a finite source effect. And the detection and the constraints to the mass-related parameters requires the high-cadence surveys. So KMTNet is such one of the high-cadence microlensing surveys. It has 12 square degree 15-minute cadence fields and operates for more than 7 years. And what's special is its 3 global sites at South Africa, Australia, and Chile, which provide nearly continuous observation within 1 day, as shown on the example. And so it intrinsically has a ideal coverage for the events less than 1 day. And for the bound planets, KMT showed a great ability to detect the low mass ones. While the lowest mass ratio Q of Ogo and Moe is about 10 to minus 4.4, the recent KMTNet result shows a low mass planet down to minus 10 to minus 5.17, which is 6 times lower than the previous results. And this is also short time scale and low amplitude signals. But what about the free-floating planets? Here I plotted the current published free-floating planet candidates with theta E measurements. The lowest theta E of KMTNet is more than 4 times larger than that in Moe and Ogo. And because the angular Einstein radius theta E is proportional to the square root of the mass, this implies around 20 times mass gap. So that is contradictory to its sensitivity on the bound planet. So if KMTNet intrinsically has the sensitivity to detect the low amplitude and extremely short timescale events, so where are the low mass free-floating planets? To understand the tension, we have to look back to the workflow of KMT. The current KMTNet image reduction process has 3 steps. First, they use the FIDI pipeline for the full-frame differential image and the photometry. This step is fast but not so accurate. And then they use the event funder to search for the microlensing events on these light curves. And this search pipeline detects around 3,000 events per year. And for these detected microlensing events, they count the stems around the source stars and use PICES, another image reduction pipeline, to produce more precise light curves of these events. And next, they search for the planet anomalies on these events by event funder. And next, for this anomalies, they reduce the image again by the PASES TLC, which is improved recently by Hong Jin Yang. And these steps can produce more precise and stable records. And this pipeline is sensitive to the bound planet detection because the microlensing signals for the of their host stars is typically last for tens of days. Although the data quality of the first step records is not so good, they can still be detected and get into the next precise reductions. But what if there is no peak of the host star? Due to the imperfect image reduction and the photometry in the first step, the scatters on the light curves can be confused with the short time scale signals. And the free floating planets, especially the low mass ones, may be buried in this noise. So to detect the potential free floating planets missed by KMTNet, we are trying to set up a new full-frame photometry pipeline based on the PASES updated by Yang. Unlike the previous pipeline, PASES pipeline, our pipeline will not only produce the high quality data for the detected events, but for all the sources and search them again. So let's start. The first step for the full-frame pipeline is to register the frames. The left panel shows previous problem. That is, some of the KMTNet previous photometry is not exactly on the source, and the photometry center shift will increase the error. So the first step, we did frame registration and to align these catalogs. Our pipeline has two steps from the equator coordinates to the raster frame for each set, and from the reference frame to the image frame for the full frame for each full frame images. And for the first step, we adopted the brightest 60,000 stars from Gaia DR3 because its observation time is close to our data, so the position will not be significantly influenced by the proper motion. And for the reference frame and the image frames, we use the image catalogs extracted by default. And we improved the cross-match algorithm to make it more accurate and robust. The residuals after the registration is shown here. The position error can be reduced to 0.1 arcsecond, which is a quarter of pixel size of KMTNet. And then we masked the known by pixels variable stars and saturated pixels as the green circles here shows. If not, they will influence the image differential result. And we still cut the full frame images to the stems so that the PSF and the background can be more uniform therein. And these stems will overlap at least 60 pixels to make sure the stars in the edge can be well processed at least once. And finally, we apply the passes pipeline to conduct the differential image and extract the light curves on these steps. So here I show an example of a no KMTNet event. The up panel is the result from the previous FLDI pipeline, and the lower pipeline. The lower panel is the same event from our pipeline. So you can clearly see the improvements that these scatters are greatly reduced. And if I add a simulated free-floating planet events to the baseline of the light curves from both pipelines, as you can see, in the previous pipeline, it will be buried into the noise, and you can hardly distinguish them. But in our new pipeline, it's much more clear, so you can discover it immediately. And currently, we have tested our pipeline on 1 year, 1 square degree KMTNet images, and extracted the light curves, the stars brighter than 17 magnitude. So we got the now we got around 500,000 effective light curves in total. And we preliminary searched on these light curve samples. We set up these thresholds here, at least, to automatically select the non-constant stars with significant bonds, and then we match them with the non-overvariable stars and removed them from our sample. Only 0.8% unknown stars will remain in these steps. And we visually check the remaining light curves and divide them into microlensing light curves, variable stars, and photometry errors. The microlensing light curves includes the non-KMTNet microlensing events, some non-OGO and MOI events, but missed by KMTNet in the previous search, and some new event candidates, and unknown events that still request multi-year data to check. Here I show some examples. This is actually the window for my visual check. The left panel is the bin, the light curve, and the right panel is the zoom in for the variable region. It's a non-OGO event, but in the previous KMTNet search, it is lost. But now we can find out it. And also there is an example of MOI FS final source events, but that is missed by KMT in the past. It is in a nearby source instead of in the of the star in our source catalog, but we still detected it because the distance is very close. And we also get some new microlensing candidates with low amplitude and large U0. Also, we found some extremely short timescale signals, but for this bump, because the KMTC, the red dots in the red still shows some variabilities. We consider it not an event caused by FIP by free-floating planets, but CV or a flyer. However, it still shows that our pipeline has enough sensitivity for the free-floating planet detection. So currently, we have set up this new full-frame photometry pipeline for the KMTNet and greatly improve the sensitivity for free-floating planets. We have tested our pipeline in 1 year, 1 square degree images, but unfortunately, we have not found convinced free-floating planets yet. And in the future, we may reduce more fields and years of KMTNet historical images, and hopefully we will find some new free-floating planets, especially the low mass ones. And our pipeline may also be applied to the other variable star search or the reduction for other images. That's all. Thank you. Any questions?
Harold, great work. I would like to know how long will it take to run your pipeline on all KMTNet data or on one system of KMTNet data? How long will it take?
Okay. For the sample I test for this 1 year, 1 square degree images, it runs for half a month in our machine, and if we consider all the data set, there is around 84 times than the previous one, but we can just increase the cores for CPUs to speed up, because the missions can parallel can be running parallel. But it's true that we missed some problems in speed, because if we extract the deeper catalog, especially for the fainter stars, the speed now is cannot be accepted yet. But we are trying to solve it, and hopefully we can improve the speed in the future. Thanks.
Any other questions?
So I may have missed, but are you conducting the photometry for only the stars registered on the reference image, or are you also detecting the new events which are not in the reference?
We only extract the records from the reference catalogs. Yeah, we did not detect we did not detect the unknown stars for this.
So there's still room to improve.
Yes.
But I know it's a very hard work.
Hi, very good topic. I will ask a similar question. Someone asked Shemek about Roman FFP candidates and KMTNet fields. I think the answer might be the same, but there will be expected KMTNet coverage.
Sorry, can you explain it?
So the oval,
yeah.
The fields may be extincted, and Scott said Roman fields are not confirmed yet. But for Roman FFP candidates, will there be? Is it expected also KMTNet's observing strategy might also cover some Roman?
Yeah, I think if they cover the same areas, that could be, but I don't know whether they will decide to set the fields of the Roman region, I think they will consider this. Yeah.